Welcome back. We are discussing about the sludge handling aspects of wastewater treatment. Now, in this video, we'll be discussing about a design example for sludge digestion. Design a sludge digester for the following data from an activated sludge process handling 500 kgs of dry solids. Primary sludge solids 5%. Digested sludge is 10% solids. Volatile solids is 60%. Volatile solids in digested sludge 70% destroyed. Specific gravity of fixed solids in both primary and digested sludge are 2.5. And specific gravity of volatile solids in primary and digested sludge, assume it as 1. And if you any missing data, you can assume. So here, one is called raw sludge. Raw sludge is nothing but here we are mentioning as primary sludge. And another one is a digested sludge. That means after the digestion in the anaerobic digester. That we are calling as this digested sludge. So this is the terminology used in this problem. This is to be remembered. So primary sludge is 5% here. This is having 5% solids. And this is 10% solids. So increment of solids by 5%. That means 5% solids means 95% moisture. 95% here moisture. And here 90% moisture. So this is the equation we have. So now first one is the weight of dry sludge. WD is equal to 500 kg per day. Because before digestion and after digestion, two cases we have to consider to find out what is the volume, and based on that, what is the volume of the digester and all those things. So first of all, we'll calculate the specific gravity of the solids in the sludge. And for the primary sludge, that is before digestion, your formula is 100 by SS is equal to percentage fixed solids by specific gravity of fixed solids, percentage volatile solids by specific gravity of fixed solids. So 100 by SS is equal to specific gravity of the solids is equal to, here what we are having primary sludge, volatile solids are 60%. So automatically the fixed solids will be 100 minus 60, 40. And then here volatile solids are 60. And given specific gravity of fixed solids primary is 2.5. So we are writing this as 2.5. And the specific gravity of volatile solids given as 1. Writing it as 1 here. So SS when calculating from this equation, it's coming out to be 1.32. Now calculating specific gravity of the sludge. Sludge contains what? This is we are having solids plus water. There is nothing but moisture content. So these two contributions we have to consider here. So solids having a specific gravity of 1.32, but primary sludge is having 5%. So 5% of solids having a specific gravity of 1.32, this percentage solids by SS. And what is the moisture content here now? 95%. And what is the water content? The specific gravity of the water is 1. So using this relation, 100 by SSL is equal to so on and so forth. Now we are calculating specific gravity of the sludge like 1.01. Now we will calculate what is the volume of the primary sludge. We have the formula WD divided by rho W SSL PS. So 100 kg per day is the dry weight, 1000 is the density, 1.01 is whatever we have calculated here, 1.01 is calculated here, and percentage of primary solids here is nothing but 5 by 100. So which is equal to 10 meter cube. So this is volume of primary sludge or We can also call this as a volume of fresh sludge. So we can write VF, anything we can write. So this is corresponds to the primary sludge. What about the secondary sludge? That is after digestion. After digestion, if you see, the dry solids are 500 kilograms. Volatile solids content is given as 60%. So 0.6 into 500, that is 300 kgs. And fixed solids content will be 40% of 500. So that's equal to 200 kgs. Now, fixed solids content will not change after digestion. Fixed solids means inorganic. So there's no change in that. But volatile solids will be destroyed in the process. It is given 70% destroyed. So therefore, 30% remaining. 30% remaining. So now what is 70% of volatile solids here? We will see. Volatile solids are found out as 300 kilograms. Out of 300, destroyed is 210 kgs, 0.7 into 300. What is remaining? Remaining is 0.3 into 300. That is 30% of this, 90 kgs. So solids after digestion will be equal to what? Fixed solids, whatever the quantity, that is not changing. And volatile solids, whatever the remaining. So what we are trying to look at here is fixed solids content we already calculated as 200 kgs. So 200 kgs here. What is remaining volatile solids? 90. So 290 kgs. So this is what the quantity of solids after digestion. Before digestion it is 500. Now it is 290. Now what is the percentage contribution of these fixed solids and volatile solids after digestion? We'll calculate. First of all, we'll calculate percentage of fixed solids. So fixed solids are 200 kgs in 290 kgs. So this is equal to 69%, right? And now what is the percentage volatile solids after digestion? 90 kgs, we already calculated remaining solids. And this is a 290, this is 290 here. And then this is a 31%. So percentage solids after digestion is a 10%. So this is what we have. So now the contribution of volatile solids is only 31%. Before digestion, it is 60%. Now it come down to 31%. Fixed solids percentage, before it is only 40%. It has improved to 69%. And the total percentage solids after digestion is 10%. Now we will calculate what is the volume of the sludge after digestion. Again, we go with the same formula. 100 by SS is equal to percentage Fs. 100 by SS is equal to percentage Fs by specific gravity of fixed solids, percentage volatile solids by specific gravity of fixed volatile solids. 100 by SS, the specific gravity of solids, is 69% is the percentage of fixed solids we have seen now, and 2.5 is specific gravity of the fixed solids. 31% is the percentage volatile solids, and this is one specific gravity is 1. So therefore, specific gravity of solids is 1.72. And now we will calculate specific gravity of the sludge. So this is nothing but solids plus water. Solids plus water. This contribution also we have to see. Water means moisture content. So percentage moisture content by specific gravity of the water, percentage solids by specific gravity of the solids. 100 by SSL is equal to 10% solids means 10% divided by specific gravity of the solids 1.72, and the remaining 90% will be water having specific gravity of 1. So that SSL is now we are calculating as 1.04. Now volume of digested sludge, we are calculating the total quantity of sludge after digestion. We have found out that 290 kgs divided by 1000, and the specific gravity of the sludge as 1.04, and solids after digestion 10% is given, 10 by 100. So this is 2.78 meter cube. So this is nothing but your volume of digested sludge. So we can also write VD. This is V2. This can also write as VD. VD stands for the volume of digested sludge. How much is reduction of volume? Initially 10, now it is 2.78. That is equal to 72% volume is reduced because of sludge digestion. So this is enormous volume. Okay. So now initial 10 meter cube, it is only 2.78 meter cube after digestion. That's why the digestion is again an integral part of sludge handling system to reduce the volume of the sludge handled after digestion. So now we will calculate the digester volume. Digester volume, we have two methods, linear variation method. In the linear variation method, what we are assuming is the variation between the fresh sludge and the digested sludge is linear for the period of digestion. So this is your fresh sludge and that is linear digested sludge. This is the time period, whatever may be the time for which the digestion is going on. So for this, we are having the formula Vf plus Vd into Td by 2 plus Vd into Tm. This is the monsoon storage. Vd is the digested sludge and Tm is the time period for monsoon. And Td is the digestion, this is a time period for digestion. So here we are assuming now Vf is nothing but V1, which is 10 meter cube, and digested sludge is nothing but V2, 2.88. The digestion period we are assuming it as 30 days, and the monsoon storage we are assuming it as a 2 months period, 60 days. Substituting all these values, we are obtaining here as 359 meter cube using linear variation methodology. So now the second model, what is the second model here? We are having a parabolic variation. In the parabolic variation, what it means is the fresh sludge is there and digested sludge is there. Instead of linear, now we are going with the parabolic variation. So this is your fresh sludge and this is your this is digested sludge. We are drawing to some scale and graph. So this is the digestion period. Instead of linear, it is now parabolic form. So for this, we are having the formula V is equal to Vf minus 2 by 3, Vf minus Vd into Td plus Vd into Tm. This is the monsoon storage and this is the volume required for sludge digestion. Substituting all these values, we obtain 323 meter cube. So here, compared to previous value, the previous value 359, now it is 323. So we obtain parabolic. Normally what we have to do is we should take higher value, but normally in the digestion period the destruction of volume from Vf to Vd is not linear, so this is a non-linear trend. That's why we generally go with the parabolic variation model, and then we go with the 323 meter cube. Sizing of the digester. So the depth of the digester usually less than 9 meters. So now I am assuming 6 meters, the minimum of 6 meters, and should not exceed 9 meters. So area of digester is nothing but volume of the digester and divided by the depth of digester, 6 meters. So 54 meters square. So now you go for circular configuration, the diameter will be around 8.3 meters. So gas production is, we are assuming 0.9 meter cube per kilogram of volatile solids destroyed. So there are two options. One is based on kilograms of volatile solids added or kilograms of volatile solids destroyed. Now in this model, I'm assuming here so much of gas generation per kilograms of volatile solids destroyed. Volatile solids destroyed, we already calculate 70% of something, 300, 210 kgs. So therefore, biogas generated will be 0.9 into 210, that is 189 meter cube per day. So this comprises of carbon dioxide and methane. So carbon dioxide is less, but methane will be around 50 to 60% of methane. 50 to 60% of methane, and the remaining will be carbon dioxide plus some other gases. Plus some other gases. So this is your methane. Methane is mainly used for the heating applications because of high calorific value. So we have to have a check here the volume of biogas generated per unit surface area of the digester. So 189 meter cube per day is the gas generated as per the assumption. And 8.3 is the diameter. So surface area pi by 4 d square, which is coming to be 3.5. It should be less than 9. So this completes the design. So let us quickly look at the shape of the digester. Now you see here depth of the digester. The depth of digester is 6 meters, where I showed here, and 8.3 meters is the diameter. This is the gas stove, and this is the gas inlet. The gas which is coming is sludge which is coming here. Sludge is coming here, and the gas is going out like this. Sometimes the gas can also be taken outside from the top, depending on the type of digester what is provided here. In this model, the gas is taken from the top through a bent pipe, 90 degrees bent pipe here. And then here bottom sludge, usually 1 is to 1. This the sludge, this is 1 is to 1 is what normally provided, or 10% minimum, 10% slope minimum. So 10% slope minimum means what? So this is your slope. So this is nothing but d by 2, where d is the diameter. So this is your y. So therefore, what we are saying is y by d by 2, y by d by 2 is equal to 10% slope. That is 10 by 100. And d is equal to 8.3 meters. So therefore, y is equal to 0.42 meters. So this is how we normally have this, the sizing of Androbit sludge digester. Okay, thank you.